Okay, let's see. So I wanted to record the Monday, like I missed Monday class, but and then I did Wednesday on the Polymer nanocomposites, and I wanted to kind of finish off the Polymer nanocomposites today or on this video. And then kind of, so I'll have then I can go through a paper on Friday. Anyway, hopefully this will work okay. Anyway, so on today, Wednesday, I went through kind of the first 8 slides of this, and the 62 total slides. I'm not sure I can do the whole thing, but we can put a dent into this. Anyway, there's kind of there's a whole bunch of different inorganic particles you can put into polymers, and then you can make those into nanoparticles. And usually you'll have like some kind of coupling. That's the idea, like some chemical coupling. So I mentioned that today. But the actual use of these materials would be something like flame retardants. So, and things like calcium carbonate, those are rock that's limestone is ground up into small pieces, right? Or silica or titania aren't necessarily this kind of model system that are used, right? So there's a disconnect between something like a tire, which is carbon black, that starts with nanoparticles, so 5 nanometer primary particles that aggregate, and then the aggregates form agglomerates, and the agglomerates will form this network. It's a phase-separated 2-phase system with no miscibilizing between the polymer and the carbon black that drives this kind of structure that leads to tear resistance, static charge dissipation, and then reduction in the or modification of the grip and the wear of the tires. It's a trade-off between those two. So anyway, when you look in the academic end of this is what you see are monodispersed spheres with chains attached to the surface to miscibilize the particles with the polymer matrix, right? You can, the main idea that's going on is you have change in the graft density on the surface of the particles, and then also change in the molecular weight of the graft versus the molecular weight of the matrix. So when this is 1, they match. If you're kind of at 1 or below 1, so when the grafts are shorter than the matrix, you get well dispersed if you have a high enough graft density. And then if the graft chains get longer than the matrix, you get phase separation. And there's also a dependence on the size of the particles and the size of the chains in the matrix, right? So there's a variety of different dependencies that affect more or less the miscibility of nanoparticles in a polymer. And if you get into this region where you have a low graft density, then you can get things like sheet strings, various structures forming. So that's of interest also. So all those things have been studied extensively, right? So, and I went through this kind of hierarchical structure in the normal aggregated filler materials. So this is where I left off. So McKay came up with this idea of the mapping out of the phase behavior, right? So this is where he's looking at varying the molecular weight of the grafted chain, and supposedly this is scattering, so it's intensity versus Q. In this thing where it's power 4, it means you have a solid object all the way to the largest sizes, so it's inverse size. So it's going up into the micron range. So power 4 means the surface scattering. And then when he gets into this more miscible regime, it's like kind of where the grafted chains get higher molecular weight, then he gets dispersion of the thing. So basically he's saying this is a dispersed, where it has basically nano-sized particles being dispersed. So that this knee is Guiney's law, and he sees independent particles there. So comparing the so there, as you add nanoparticles to the matrix, he can tag the chains with deuterium and look at the size of the matrix chains versus matrix chains with no. So it'd be 1 when you have no filler in the system. And if you add nanoparticles to it, if they're in this miscible regime, the chain size gets larger, meaning there's a compatibility between the chains and the nanoparticles. It's acting as a diluent for the let's see, why did that guy do that? For the polymer. So it's acting as if it's a solvent for the polymer. So I want this thing down here that I can't get to. Like that. So let's see if that thing stays active. All right, so anyway, so McKay worked that through the interaction parameter, how it would be for a polymer. So this is per mer unit enthalpy times n gives the per chain. So the chain insertion enthalpy. If it's a nanoparticle, then it's got to do with the surface area. So it's the surface area interaction. You can write expressions for the free energy of mixing and talk about kind of a Flory-Huggins thermodynamics of the mixing of the nanoparticles. And then McKay also came up with this idea that if you have small particles, there's a lot of this orange interaction between the particles versus the interaction between the particles and the matrix. So these particles are confined in that region, and that's going to lead to changes in the free energy that can be modeled to understand why nanoparticles, the dispersion of nanoparticles by this kind of structural model, this orange region is this AU, or let's see, okay, there's 2 areas. There's the green area and there's the orange area. So the 2 things contribute differently to the free energy. So the AU is the orange and the AC is the other green part of the thing. And when the particles get smaller, you get more of the orange than the green. So then that shifts the stability of the system, right? The thermodynamic stability. All right, so he made a model based on that ended up giving him this map where you have as the matrix gets larger, then you get more miscibility and you get immiscible with the, depending on the nanoparticle size and the polymer size, he can predict this miscibility and miscibility map. And that was the first, 2006 was like the first mapping of particle. And you can see the particle size affects the fraction of orange versus green in this. And that's where he gets this kind of mapping out. The particles are never really miscible, right? Because they're not, miscibility implies you have molecular mixing, and there's no molecular mixing if they're nanoparticles. They're too large to have that kind of mixing going on. There's a little bit of a stretching of what's actually going on in the systems. So McKay was originally at Australia, then went to Michigan, and then went to, so Michigan was all Tutuja is also at Michigan. He's doing surface modification for ice repellency now. And then he went to Delaware, University of Delaware. And this is Shadler, who was at RPI, and Sanat Kumar was also at RPI, and then he moved to Columbia. And this Ben Nikowitz is also like a chemist that works with them, who I think was at South Carolina. So it's basically that's kind of a team that was formed in the early 2000s. Then Kumar went off on his own, more or less, to Columbia. But why nanoparticles? This is like a review for Materials Research Society. And then it's basically, they have a lot of surface area. So they basically can get different properties because there's no defects in a particle that's smaller than the critical flaw size. So they're stronger than a larger particle. They have a huge amount of surface area. So things like bound polymer chains at the interface, since it's all interface, you can get this huge amount of per mass of material you add of this kind of material that's affected by the interfacial. Okay, we'll see that the glass transition shifts at the interface of a particle. They can add, you can add, sometimes it's advantageous to add defects to a system, like in a high impact polystyrene where you want to introduce flaws that actually give the material more strength, right? So it's basically some advantages to introducing defects. And then there's also this issue that the materials themselves, so say the optical absorption range in the UV vis absorption for gold particles shifts directly with the particle size. So you can tune the absorbance of a gold nanoparticle polymer nanocomposite, and that can be used to as a catalyst, or it can be used as a way to tuned absorption for different optical properties. Right, so the properties of these nanoparticles change with size, and the interesting part is when you get to particles smaller than like 100 nanometer, and then things really start changing rapidly. So you can get tuned properties by using nanoparticles. That's one thing that people are interested in. So this is when a chains get near an interface, so there's some confinement of the chain, and that leads to a shift in the glass transition. Right, so you can see this is silica and polystyrene, and as the particle spacing gets smaller, you get a large shift in the glass transition, 20-degree shift, right? And then you can also get a larger glass transition depending on what happens with the so if the glass transition drops, then the material becomes stiffer. Then basically the nanoparticles having the effect of change, not just the particle itself has a high modulus like silica, but the polymer near the nanoparticle has a significantly higher modulus than the matrix polymer, right? So there's an enhancement, and if you have more surface area, this is taking up more of the bulk material, then you have a larger shift in the properties of the material. This is solubility parameter. So the difference in the solubility parameter squared is proportional to the chi, the interaction parameter, the enthalpy of interaction. So if with a TG shift, you get a change in this solubility parameter difference, and then that can drive miscibility between the nanoparticle. So he says wet and de-wetting, right? If you have a negative shift, so it becomes more miscible. So you have a chi that becomes negative, then you get wetting, and then it's 0. Doesn't wet, but if it gets positive, you get de-wetting, like positive chi, basically, is what you're talking about. And again, you see it's that del times the surface area, like in the McKay equation here, wherever that is, where he says he's gonna swap out surface area times chi instead of number times chi for nanoparticles. So this is the effective interaction. There was a surface area times chi versus the graph chain length, and then he's just showing that for different these are different particle sizes, and then with different sigmas is the surface number of chains per surface, so per fixed surface area, like per nanometer squared. So the bottom one has the higher chain density on the surface. This has the lower chain density, and they're all showing the same kind of behavior with particle size. That as the particles get smaller, you get a bigger shift in the miscibility. So more miscible, better interactions between the particles and the polymer matrix. So this is for a matrix of 110,000 grams per mole, and it's looking at as you add silica, so silica with grafted chains at the surface, and these are the graft lengths on the surface for a fixed density of chains. So basically, with the higher ones, higher molecular weight grafted chains, so when it gets above the 110 for the matrix, they de-wet, and when it gets below the 110 for the matrix, they wet. And then it's a linear function in the concentration of silica in the system. And then this other one is that the shift in the glass transition for the various for the 3 different molecular weights of the matrix versus the graphs. This is 1 over the other number that was being used. So this would be 1/3. This would be like 2, right? Or so it's basically for those 3, you get a linear dependence in this delta, the glass transition shift versus the 200, 400. Let's see, B, the change in glass transition function of the graph densities. This is sigma. So this is the graph density here. Sigma times the graph molecular weight, but basically the graph density. I'm something like the graph density, right? And showing linear dependence in the wetting, de-wetting. So you can kind of see, I guess you can see where this is going. Like you have these parameters that you can change to map out, and there's some things that you can measure as a response to those parameter changes, and you map those out and get dependencies and try to explain it in terms of Flory-Huggins theory, right? That's kind of what the game is here. So this is Krista Morty, who's a researcher at University of Houston. He's a rheologist, basically, but then he's looking at carbon nanotubes in I think in polystyrene. No, sorry, polycarbonate. So he calls it bisphenol A as polycarbonate. So that's using this this monomer as a condensation reaction with phosgene, which is nerve gas, right? So phosgene is this OH, and the carbonyl. Then that will react with this and water comes off. And then you can make polycarbonate. That would be what he calls bisphenol A. And then there's also bisphenol F that doesn't have these two methyl groups on it. So these are those two here. And then the other one's polyethylene oxide, like the water-soluble polymer, mixed with carbon nanotubes. So he's saying from this plot, so this is a scattering plot, intensity divided by concentration versus Q, and he says he puts all of his bisphenol A at different concentrations. He says he can get a master curve from that, and then he gets surface scattering, some primary particle size, and then kind of a fractal scaling, and then he determines the screening size from that. So the screening size is, I think I mentioned this before, as the concentration increases, you can't see the kind of aggregates anymore, so that gets washed out, and the point where it gets washed out, 2 pi over the Q value where it gets washed out, as you increase the concentration, is this mesh size, which is like the size of the mesh that the particles make. Right, so he's mapping that mesh size versus the concentration. And it shouldn't be linear because it's going to depend on the fractal structure of these things. So the way the size changes is going to depend on the fractal dimension of the particles you're putting in. In this case, there's some odd shaped aggregates which aren't really well defined. Right, but he gets this kind of behavior. As the concentration increases, mesh size decreases, and that's what you'd expect from this. Anyway, and then he also does the dynamic mechanical properties of this, but I didn't put that in here. Anyway, so there's this idea about the interface. So this is Kumar again from Columbia, and then and a group of people, I don't know who the others are. This is from 2013, so 6 years later, and basically talking about this interfacial features here. So if you take the polymers, so you mix a polymer with nanoparticles, and then that aren't surface grafted, and then you take it out of that and put it into a solvent and wash away the polymer. There's still some polymer stuck to the particles. So you can stick that into a thermogravimetric analysis and burn the polymer, see the weight change, and say the thickness of the interface would be if that was the density of the polymer times the amount that burned off. Right, so that would be a TGA number of this thing. So that's his TGA graft thickness here. Okay, but he says he can get a much higher graft thickness. So that's not the point of this paper is that graft thickness, I guess it's called bound polymer layer in nanocomposites. It's kind of a generic name. All these papers have like 1,000 citations, by the way. So they're all like highly cited. Anyway, so basically the TGA size is too small because the chains are actually not just stuck to the surface, but they're swollen, right? So when they're in the matrix, we can measure that by doing either measuring the interaction potential through this area and the chi thing that was before that McKay developed, or you can do it through the dynamic light scattering. So he gets the hydrodynamic radius, and that gives him this del, when he subtracts the particle radius, they're both spherical radii, so the hydrodynamic radius should work as a radius, and then he gets a larger number when he does that, because the chains aren't just compressed down into a layer, they're actually kind of swollen into the melt. So he shows this by two methods, right? So people are interested in the interface. So the interface, this is a Chinese group. I don't know who this group is. The web doesn't sound Chinese, but anyway, I don't know who this is, but basically this is the popular picture of it. Like they call this mushroom. So as if you just have these blooms of polymer at the surface, that'll be a low graph density. So a few chains on the surface. And this intermediate semi-dilute polymer brush regime where you get kind of straightened out chains. None of this has really been measured, right? So this is just cartoons that people have made. Then at high graph density, supposedly you get a lot of straightening out chains, and then this. So you wonder, like, how could you possibly do this? Like, in other words, you have to synthetically make this thing. So how are you going to do that? You're going to take a chain that's out here, got a lot of entropy, then somehow you're going to drive it to the surface, straighten it out spontaneously, and have it react and have like rods, right? So that's unlikely to happen, right? In other words, that would be impossible to do. So how you get to this model, how you would actually make that model is pretty hard to see. So nonetheless, this is the cartoon that people are using, right? And it's based on the cotton, the Dowd cotton model for star polymers that we mentioned briefly earlier on. Anyway, so that's kind of a cartoon of what people are thinking about the interface of a polymer nanocomposite would look like. And this is just all right. So that's just there to show you that you'll see that theme over and over again, and simulations, everything else, right? So that's just there to show you that. This is just showing this idea of aggregates, sheets, chains, and then dispersed kind of particles, right? As a function of the size of the particle versus the coil size of the chain. And this is the graph density in this axis, right? So that you can see these kind of, you can see the evidence for these regimes are these micrographs. That's it. So tell me which one of these is a sheet, like without the words here. Like, is that a sheet or is that a sheet? So you can't tell. So basically this is just begins with this kind of McKay thing, and then the Sanat Kumar, and then kind of grows out of that, right? So whether this is really sheets and chains is pretty hard to tell. And the evidence is going to be given by, well, there isn't, the evidence is kind of in the scattering. I'll show you, it isn't that great. So you can see again, like circular aggregate sheets, strings, dispersed, the same kind of story. And this is simulate part of, this is a huge group, right? So Jack Douglas is a simulation guy, famous simulation guy from NIST. Colby is the guy that wrote the polymer physics book, one of the authors, Penn State. Diaga's at Argonne, now he's at Department of Energy, and now he's at NIST, right? So he's got 1,000 papers in various areas of polymers and biophysics, and neutron scattering stuff. Orlovsky's an X-ray guy from Argonne. I don't know who this is. Don't know them. And then Shadler is now Dean of Engineering at University of Vermont, but she was at RPI. This is her chemist from University of South Carolina. And Sanat Kumar at Columbia, and Akora, I think, was Kumar's student, and she's at Stevens Institute, New Jersey. So this is an all-star paper in Nature Materials, right? It's like a review, anthropic self-assemblies. It's got some simulation things showing, yes, we can get strings, we can get sheets, we can get whatever we want. And then this is some experimental showing like these regimes of the graph density and then the chain length. It's the same plots, right? Kind of done in different ways. So whatever you normalize the x-axis by. So that same kind of picture of kind of like a phase diagram, right? So this is some of the evidence for the phase diagram, like micrographs and the scattering. So the scattering kind of interests me. I mean, some of these actually look like sheets, right? So in this, I don't know. Anyway, you can think about it. Like you can make your own opinion about these things. So scattering intensity versus Q, we know that -1 would be a rod, -2 would be a sheet, -4 would be a surface. right? So this is their evidence for sheets, rods, and coils or something, right? So dispersed. So power one, that doesn't exist here really, or maybe here. Then in this case, higher graph density, there's no, I mean, whatever you want to pick out from this is pretty hard to tell, because this hump out here is the spherical primary particle, the particle that they have that's going to assemble into sheets and rods. So expect it lower than that knee, which is kind of the size of the particle. You're going to see these power laws show up, right? So here, maybe you can see that it goes to 2 for the green one, maybe, and then maybe this one's 1, maybe that, it's pretty hard to tell kind of what's going on here. They make their claims about it. And whether these size scales, 10 to the minus 2 is 100 to 10 nanometers, right? So whether the size scales match up with whatever they had in the micrograph. Oops, let me get here. So is 10 nanometers going to match up with their sheets here? That's the question, So it's not, this is 500 nanometers, that bar, right? So 10 nanometers would be a small piece of that bar. So it's kind of hard to see like where 10 nanometers is in these pictures, right? So anyway, that's the kind of thing you could do to look at this. They make their own opinion. You can make your opinion about what's actually there. When these things get dense, though, I mean, they form networks. Like they're going to form some kind of network structure. So then you want to say, well, if you go to rheology, a network structure, the G prime and G double prime are going to have a power law dependence. So log will be a straight line, and they should have the same power law dependence. If you look like it within the circle, the solid and hollow circles, red, have that behavior. So you'd say that's a network on a large scale because it's low frequency, and something similar happens on a small scale here. Right, so high frequency is small scale, this is large scale, there's two kind of networks forming in that system. So the red, those are large sheets. So it's possible sheets can form networks, so that could be a consistent story. And then if you, instead of going against frequency, if you increase, see, this is a low angle or low, small deviation, so small strain oscillatory rheometry, right? So like less than 1% strain. And then if you go to start with 1% and then go to 10, 100, 1,000 strain with the same measurement, the same oscillatory, so you get these wide swings at whatever frequency they have here, 0.1 inverse second. So then you see yield points, which means the network, if you had a network like that, then you see a yield point happening. So the thing fails. So that's kind of an evidence that you have some kind of network existing in the thing. And the same with blue. So red filled is the large sheets, and then blue is also sheets, I think. So basically it's a different molecular weight matrix, same thing, same sheets. And then the black is short strings. So the short strings have an enhanced modulus, but they don't show this yield point. I guess that's the point of this. So basically the sheets are forming a network that has a yield point. So that's kind of interesting. I mean, this is actually the strongest evidence that they have for these things going on. Then and this is Sanat Kumar, the Columbia guy again, and then with the chemist, South Carolina chemist, and then nanocomposites, kind of what pathways you could take. So you could have graphs that are homopolymers, you could put copolymer graphs on if you wanted for some reason. And Benikowitz has done that. Like he's done extensive modifications of particles, right, like that. And then if you have homopolymers, you can do a dense brush or you can do a sparse brush. And then he's saying that's like a surfactant, and this is something else. Like this is where the chains straighten out, and this is a mushroom thing. And then same Prussian matrix different, so you can mess around with a lot of, so all these things have been studied. That's kind of the point of this. Anyway, and then if you, like, this is what Benikowitz does, like he does this kind of silane coupling. So you have a silica particle, you do a silane coupling to it with an amine N group on it, and the amine N group can couple with this sulfate group. So you end up with this functional group that can be used in a RAF polymerization, which is like a have a monodispersed free radical polymerization. Right, so yeah, you have a radical that's protected, and then you can attack that and make polystyrene or PMMA or other vinyl polymers off this. And then you can, at that point, you can terminate that, and then you can start another raft to get short and long chains, right? And then you can get this kind of weird looking spider out of it, right? You can do a lot of other different things. So he's done like, I don't have many. So he's done like a huge number of these types of different kinds of grafted nanoparticle, monodispersed nanoparticle systems, right? This is from this paper, right? So these are perfect spheres. So you get this oscillation due to this perfect sphere. And then they're claiming that this has a polymeric, so continuous lines are best fits to a Gaussian chain model. In other words, you have this particle, and then the chains that are stuck to it are Gaussian, meaning it's a mushroom. It's a mushroom model, low graph density, right? And then this is supposedly where you have a core and shell model, which would be the high graph density. So that would be like wherever that was. So the one is this mushroom, the other one's like this one over here, right, between those two. So wherever that is here. So I guess it's saying that because it's -2, that's Gaussian. I mean, the funny thing is, like, if you draw a -2, you have the same thing here, right? This should be -4 if it's really core shell. There's no -4 there. So that kind of makes you wonder what's going on. There's a size difference in the thickness of the interface and things, but they use two different models to fit these. So the size difference can just be, anyway, it's probably pretty good work, but you can critique it also. And in this paper, the same paper, they come up with that plot that I first showed you, that's like graph density and then versus alpha is the ratio of the molecular weights. And you can map out the entire thing. And this was from 2013. So it's one of the early, this paper is cited like 1,000 times, right? So this is a high citation paper. This is a similar paper by the Akora, Shatler, and Sanat Kumar, right? So, and then TI, this is that long paper from Nature Materials showing the different structures you can get. All right, so what else? So then people talk about transport. So this is quasi-elastic neutron scattering, like what John Nichols talked about for dispersed and aggregated nanoparticles, right? So its diffusion coefficient follows Stokes-Einstein. Diffusion coefficient should be proportional to KT as long as the radius of the particles doesn't change. And then the mean square displacement, so the square of the x squared is going to be the definition of the diffusion coefficient. This is Brownian motion. So this x squared should go with temperature linear, right? If everything was fair, if the RH is fixed. So it's linear as you go along. You reach a temperature and boom, it kind of like takes off. So you get a larger displacement than what you're expecting. And that would generally mean that the RH is smaller than what you're expecting. In other words, RH is dropped when you reach that temperature. And then so when you reach that temperature, maybe the structure is changing. So you've reached a point where something happens to the nanoparticles, right? But there is a linear part to this thing. This is that same system, kind of what it looks like. It's a micrograph of it. And this is the same system like TEM of that system. So again, like stress and strain as a yield point. So that the network particles, what they call network, has a strong yield point. The sheets have a weaker yield point. And the agglomerated, which is has no yield point. That's kind of the point. So there's no network formed in the agglomerated system. A network is a good thing here. That's the G prime plot that associates with that at low strain. Like if you just do 1 degree strain or 0.1 degree strain, something down here. So So that you can see that there's like a common theme to what stuff is. Same thing, graph density versus the ratio of graph chain length to matrix length. Just another paper doing the same thing. This is different though. So this is actually the properties, right? So this is the first thing where people have actually looked like, what's the impact of all this stuff on what's going on. So you have elastic modulus, yield stress, and fracture strains. Those are useful properties. So you can see 175%. So that's like doubling. That's twice, right? Twice the fracture strain if you have low graph density. Let's see. This is the low graph to matrix molecular weight, and then low graph density, both, because you get no elastic modulus because you don't have much. Well, you get low elastic modulus and because low graph chains, so basically no graph chains. Yield stress drops, and you get double the fracture strain. So the thing elongates better with just basically bare particles. Right, so the bare particles have some benefit. You're getting twice the fracture strength. Then as you add denser particles, so in this region, he calls it the jam state. In the jam state, you can enhance modulus, but you get a worse yield stress and a much worse fracture strain. Then if you go to the upper right corner, you have a huge gain, like 3 times the fracture strain. You have an increased yield stress, and you also have an increase in the elastic modulus. So this is high chain density, and you have kind of the graph chains are longer than the matrix chains. So he's calling that dispersed. Right? And then when you get strings, you can get tuning properties here. That's kind of the idea. You can tune the properties, pick the properties you want, and then tune these things like chain density and the graph to matrix molecular weights. This is probably the most important plot of the whole thing. It's the only one that really says, not just like looking at kind of this constitutive properties, like you change a chain and something happens, but actually like the properties that you want, something you're interested in, mechanical properties. This is kind of the same paper, like optical properties. So they have, this is Berkowitz. He did the bimodal. Bimodal means this thing, wherever that is, this thing. Like he's got a bimodal to 2 chain lengths on the graphs. And then what do the things just look like at that point? So monomodal and bimodal, and there's differences in the behavior of the systems. The bimodal is clear for the most part, and the monomodal isn't. Right? So this is titania, and I think it's in PDMS. So siloxane polymer, silicone rubber. So this is an unusual additive to PDMS. Usually you'd use silica. Like silica is cheaper and it's more compatible. It's an SiO polymer. Right? So anyway, so this is just showing also that as the matrix molecular weight gets higher, you get this kind of phase separation happening. So it's got, and then these are the graph lengths on it: 1K, 5K, 10K, 36K. So the matched, this is where the matrix gets higher, and this is where the matrix is lower. So you get single phase here, and then no phase separation there. Then these are all 36K, and then this is varied. So where they match is kind of where the matrix is higher. So matrix is lower, you get single phase, and then you get kind of phase separation when the matrix is larger than the graph size. So anyway, so there's variety of things you can do here. This is just showing that you can take, so this is a Chinese group, right? Actually, all Chinese, right? So this is actually in China. So showing that you can take this kind of, so this is a copolymer. So this is like a Berkowitz copolymer. So you can see this like red and blue. And with the red and blue, they're able to do self-assembly, tune self-assembly. And basically they're growing tubes out of these beads using some kind of cyclic hydration process. Right, so you can see they're tuning the sizes versus the molecular weight of the blocks, and they can get assembly into these tubes. Right, they have SEMs to show it. So this does lead to some kind of properties that are of use. This is a different group, also Chinese, kind of looking at kind of the assemblies you can do with these particles, right? Kind of a little bit more application oriented and how the interfaces change. So probably the best, we'll look at a paper on Friday, and that's going to be an easier way to kind of understand or kind of get a grip on some of the main themes that are going on in this area. And this is a common theme, is like biomimetic, like trying to copy biology. So this is a paper, I didn't put the reference here, but this is a review paper on how you can do this with nanoparticles, right? How do you kind of build these kind of schemes of layered structures, for instance, or fibrillar structures, and improve strength and then surface properties with nanoparticles, polymer nanoparticle composites, which all these things up here are, right? So this is a review paper from 2020 by Winey, the University of Pennsylvania person. And I guess Bailey is also, I'm not sure who Bailey is, but might be a grad student, I'm not sure. Anyway, so it's just looking at the different dynamics. The funny thing is that Winey's husband, so Russ Composto, does a lot of dynamics measurements like this. So it's kind of odd that she wrote the review paper on this. She's more of a originally was a kind of SEM person, so anyway, so nonetheless, here this is. So they both have been collaborating with groups that do this dynamic stuff also in simulations and things. So anyway, so these are the dynamics that are involved. They're just listing versus on the time scale, like fast dynamics, slow dynamics. Green is the segmental motion. So that's a fast dynamics, just the monomers or the Kuhn units moving around laterally versus the chain. Then there's the intermediate dynamics of the chain, like kind of glass transition things. So groups of like 9 or 10 or 11 Kuhn units have to coordinate in motion to give glass transition. And then the whole chain diffusions, that's going to be a much slower process. That's like reptation. Then nanoparticle motion can cover the entire gamut. That's what they're kind of showing in this graphic. So each of these is going to be measured by a different technique, right? Because they're crossing a wide time scale in this. I mean, it could be all measured, all of them could be measured with dynamic mechanical measurement. But if you're going to use some kind of scattering or dynamic light scattering or that kind of technique, then each one is going to have a separate technique to look at it. So this is just showing a mapping, like the quasi-elastic neutron scattering is this very short time motion. So maybe the lateral motion of the monomers, and then neutron spin echo measurement overlaps kind of with that. And this is broad dielectric spectroscopy is going to look here, and then dynamic mechanical, that's kind of the oscillatory shear measurement. And then the TMDSC, temperature modulated DSC. So that's where you come in with a temperature that oscillates in DSC, and you can get a measurement for some relaxations there. Some alpha relaxations, like a chain relaxation, like kind of a glass transition thing or something, but so side chain motion. Anyway, so the mapping is here. So you'd expect this is following an Arrhenius behavior, right? Which would be energy over KT minus energy over KT. And this would be log of the time. So time goes with time 0 times exponential minus energy over KT, right? Then you expect this to be a straight line, bottom line, right? And you expect that as you went to higher temperature, you get lower times. So higher temperatures to the left here. So you expect a straight line that would go like that. The reason you don't get a straight line here is because these are all different mechanisms. Like they're different things are going on at the different size scales. So it doesn't make a straight line. In fact, drawing a line through this at all is a little weird. like you probably wouldn't expect. Like the green ones could be a line. Maybe part of the blue ones is a line, right? So with the red, and then there's another line here. So because you're looking at all these different relaxations at different temperatures across the scale, different taus, right? So anyway, so that's kind of the idea of the dynamics, looking at the dynamics chains. And there's these issues, the same issues, right? Like you have your nanoparticle and the matrix, that's two relaxation times. Or I mean, the polymer has all this whole slew of relaxation times, but you could have like the bound polymer layer, so you're going to have some kind of different time relaxation for that layer versus the matrix, and including all these different aspects of that layer, right? All those three different aspects of that layer. And then you could have a gradient where you don't have a discrete time for each of the components of it, right? So again, this is a whole area where people are kind of studying these things. This is some data looking at this. Again, you're expecting a straight line in this plot, and you see a curvature because you have multiple phenomenon going on in it, right? Different relaxation times. And then this kind of boundary business can get more involved. Like you have an absorbed chain. So this is without grafting layers. You have an absorbed chain, they have free chains. And then you can have this boundary layer where you have the chains mixing. So the matrix chains and the bound chains can have like entanglements with each other, slow down the free chains. And then you can have if you get to higher concentration of nanoparticles, you get the thing like we saw with the wine glass effect, the Magnoni effect, where you're squeezing out the polymer in the middle between the particles. That leads to kind of a concentration gradient. I mean, a lot of things can happen, right? You can have actually the chains that are bound to the surface of the two polymers can interact with each other, right? Or entangle with each other. Or you could have a layer between the two. So you can see like this can be a lot of different things. And who knows where this is going to actually, because it gets to be pretty complicated as a model. And how would you get really evidence to show that, except that you could do computer simulations to show it, right? So anyway, so this is just looking at, so M is somehow they call M the fragility, but M as a fragility shouldn't be a value of 300. So I'm not sure what M is here. I'd have to go back and look in the paper. But basically, this is something like the fragility of the glass transition as a function of nanoparticle concentration. It should be a number like 1 or 2, not 300. Then this is the heat capacity of the system for two different polymers and two different nanoparticles mixed, right? So anyway, this is just kind of showing, mapping out what you can look at in terms of the dynamics of the system, mapping the relaxation time for different surface grafting concentrations, and then the distance. So basically just looking at this as a probe distance from the nanoparticle interface. So this would be like a reflectivity measurement, right? So the diffusion constant. So one way, this is a Quinn's measurement where you get a peak and you measure the breadth of the peak to get the R squared, and you can plot that versus time to get the diffusion coefficient. Then basically to do the diffusion measurements, this is just showing how that's done. So you take two systems. One would be maybe deuterated and hydrogenous. Then you can use an IR beam across this to get the concentration profile, because deuterium and hydrogen have different IR signals because the mass is twice as much, so it shifts the frequency, the absorption frequency by half or something. But so you can see in IR deuterium and hydrogenous. You can watch the things diffuse across. From the shape of this exponential decay, you can get the diffusion coefficient as the argument of it, right? And that's a solid state measurement of the chain diffusion. This is what Russ Composto, Karen Winey's husband, does a lot of. He does that kind of measurement with they can use SIMS to etch into this to get the concentrations, and he uses Rutherford backscattering, where they also kind of get into the material, ablate the material and see the composition, I think. I'm not really sure exactly how that works. But anyway, you can map out the diffusion coefficient as a function of kind of depth to the particle and get this profile of what the surface looks like, which looks a lot like the like this one, the right-hand one, where you have a diffuse interface. So you can see there's a lot to this, and people have spent a lot of time kind of looking at various aspects of the nanoparticles, like and the kinetic part is probably the most difficult part of the whole thing, and linking the kinetic part back to the and you can see like all the models we looked at in dynamics show up here again, right? And as a function of like molecular weight of the graft polymer. So with all the parameters that you have to look at, I mean, in other words, when there's no entanglements, you get a high diffusion coefficient. And when the entanglements show up, the diffusion coefficient drops, right? As a function of nanoparticle size versus the tube diameter from the polymer matrix. So how is it that if you match out the tube diameter, the particles can move around freely when they're small, and then you get to the tube diameter and suddenly the particles are stuck, so the diffusion coefficient dramatically drops. This is almost like a probe to see the tube diameter from this thing. Anyway, so you can see there's a lot of kind of interesting things to look at here. So we'll look at one paper or a couple papers for the homework on Friday, and then next week maybe might look at the membrane stuff, I think. But okay, so that's about it for this. If you have any questions, email me. Thanks.